In this video, we're going to discuss the 2K factorial design, some of the different aspects that are related to it, in preparation for our final topic, which will be the fractional factorial design. So first of all, something to note is that unlike the previous few designs that we've been talking about, the 2K isn't particularly different than what we talked about in the last chapter. So in the last chapter, we had talked about the general factorial design. In this case, the 2K is a special case of that general factorial design. In fact, I say the last chapter, it's really the last slide deck. This is the same chapter where we're talking about these. Now in the 2K design, the K represents the number of factors. So think about like the one-way ANOVA was one factor, the two-way ANOVA was two factors. K is the number of independent variables we have that we care about, and they are all at two levels. So the total number of treatment combinations is 2 to the K, thus the 2K factorial design. Now, because for each factor we're just going to have a low because in each factor we just have two factor levels, we're going to tend to have a low and a high factor level. Tends to be how we treat this. We'll actually talk about this later on in this slide deck. How do we select these, and maybe a rule of thumb or something to think about. These could be quantitative or qualitative, but what you're looking for is something that's kind of at one end of the spectrum and something that's kind of at the other end of the spectrum when you're looking at levels of this. And again, we'll talk about it later. So these are used very widely. They're used for a variety of different reasons, but in industrial experimentation, primarily these are used to figure out what factors should we be looking at. So to explore a whole bunch of factors very quickly. So these are basic building block. In fact, the only reason we're talking about this was meant to be a very quick run through of the 2K design. It's just so that we can get to the fractional factorial design, which is very cool. It may or may not be quick. We won't cut it short arbitrarily, but again, this is, if I could have skipped this section, I would. This is something building up to something cool that I was hoping we get to in this semester. And then there's some special shortcut methods for analysis. We won't really talk about these too much. We'll just lean on our traditional analytic approach. In fact, we won't even have an R video associated with this, because the analysis of this design is just like the analysis of the regular factorial design, because this is a regular factorial design. It's just that now each of our factors have two levels instead of however many levels they would have had, A or B or whatever. All right, so the simple case, the 2 to the 2 design. So we've got two factors, K equal to 2. So factor A, in this case, reactant concentration, low and high. Now these are set at the two different levels, and then amount of the catalyst at low and high. Note what's going on here, that when we have high for reactant concentration, we're going to be giving each run with, we'll call it the letter. So in this particular case, the letter for being high on A is going to be a lowercase a, so both of these factors are going to have a lowercase a involved. But with a low, it's not going to have that A involved. Same thing with B. When B is high, we're going to have the B involved, so B and AB. When B is low, there's going to be no B involved. So when we're looking at the different runs, you'll see 1, which means low levels of all factors, B, which means a low level of A, a high level of B, AB, which means a high level of A, a high level of B, and just A, which means a high level of A and a low level of B. Pluses and minuses, or minus is definitely going to denote low, plus is going to denote high levels. And as this mentions, these are arbitrary terms you really do get to pick, though there are better and worse choices, and again, we'll talk about it later on. So within this, one of the interesting things to look at is how this is constructed. Now, we can definitely have replications here, but these pluses and minuses are a very, very common way to construct this. And in fact, in the middle of the slide deck, we'll get to the whole point of why we're even talking about this chapter at all. And it has to do with these pluses and minuses. So this is important. And again, you see that when both of these are minus, both A and B are going to be low, and then we're going to do replications there. When both are plus, both A and B are high, we're going to do replications there. And then, of course, there's a mix. So our primary goal is to estimate these factor effects. We're going to put together a model if we have replication. We're going to use the full model. An unreplicated design, we are going to briefly just mention that you can use PP plots here. We're not even going to talk about how. Please see your textbook for more. We're going to do some statistical testing with ANOVA. The textbook talks about refining the model in this type of experimental design. This makes a little bit more sense, but I will throw a big red flag here in generic research and statistics in refining the model in the ways that we talk about in this section. So be very careful on this particular point when we get there. Looking at the residuals, of course, is always important, and interpreting the results. Now, in general, when we have in replications, we can use these formulas to solve for the effect of A, B, and the interaction. Now, note that these formulas are exactly what we've been doing earlier. This looks fancy, but it's not particularly. If we have these different effect estimates, especially because they're all on the same scale, they're all using the same outcome, what you can determine here is looking at these relative to one another. So the difference between high and low in A is 8.33. The difference between high and low in B is -5. And then the AB interaction effect is 1.67. So practical interpretation, we see AB is smaller than the main effects of A and B. So the interaction term, it's not necessarily 0, but it seems to be relatively small. Looks like the lower level of B is higher on the independent variable than the high level of B, giving it the negative effect. And then A has the largest effect out of all 3 of these. So we can look in our table, look at the percent contribution. We see that that's echoed in what we just said, and then look at our statistic, and we see that A and B are statistically significant. The interaction isn't. Recall that when we're interpreting, we look at the interaction term first. Interaction is not statistically significant, so we can go and interpret the main effects of A and B. There appears to be an effect of A, there appears to be an effect of B, and that's how we would interpret this, as we would interpret A and B within the context. Looking at our residuals, we don't see any issues. Now, one interesting thing to think about in terms of power, I know we've talked about power already, but when we're doing these types of studies where we're trying to discover which factors we should be including, a traditional power analysis for an overall study kind of changes in some ways. So one of the things to think about is that though we might normally stick our type 1 error rate at this alpha equals 0.05, because normally the type 1 error rate's the very bad thing. When we fix our type 1 error rate like that, using a smaller number of runs, that's going to highly limit our power. Now, in this particular case, when we're trying to explore different factors that could have an effect, so we're really just trying to identify things, type 1 error might actually be worse than it normally is. So in this particular case, failing to identify a factor is very problematic. So to prevent that, sometimes we are willing to consider these higher type 1 errors, maybe 0.10 or 0.20 in these types of studies. And again, in this slide deck, we're going to have several times where I'm going to say, hey, this is okay in these types of studies. This is one of them. In these types of studies, we might consider doing this. In general statistics, and unless you have a really, really good reason, this is a really good reason, but in general statistics, we tend to stick with this alpha equals 0.05. But for these types of studies, the 0.10 or 0.20 actually does kind of make sense to bump up there, just so that we can make sure that we're discovering those factors that are of interest. So here's a description as we bump up the type 1 error. Recall that also increases the power rate. So using an alpha equals 0.10, we have a power of 75%. 0.20 increases power to 89%. So these powers are looking better. And of course, we already know this based on our discussion of power analysis earlier in the course. Now, as you're looking into a 3-factor design, again, we've got factor A, factor B, and factor C. And every time you see a plus sign on factor A, you're going to have the little a involved. So we see a little a, a little a, a little a, a little a. So whenever the plus sign is here on A, that run is going to have the little a involved. And this little Latin notation is how we denote what factors are at the high levels in a particular run. So again, previously we had the single 1. It's kind of our identity. In this particular case, that single 1 is going to say low levels of all factors. A is going to say a low level of B and C, just a high level of A. And again, if we read this, factor B for this close bottom right-hand corner, factor A is high, factor B, though, is low, and factor C is low. So we see that just factor A is high. For factor A, B, and C, we have factor A being at the high level, factor B being at the high level, and factor C being at the high level. So for the far top right-hand corner, A, B, and C indicates that all factors are at their high level. So these lowercase Latin characters tell you which of the factors are at the high level, and then by absence, they tell you which of the factors are at the low level. Now we can look at the different effects. Now it's kind of nice. I really like these visuals from the textbook, but these are kind of the different calculations, equations. The equations are much longer and more complicated. The pictures are actually a lot easier to interpret. So A, if we look back on the previous slide, the low level is all of these dots on the left-hand side. The high level is all the dots on the right-hand side. So when we're looking at the factor effects for A, we simply look at the low level versus the high level effects. That's all we have to do. When we look at the factor effects for B, we look at the forward versus the backward facing sides. And that's all we're looking at. When we look at the main effects for B, we just calculate the average on the back end, the average on the front end, and subtract. And then C, we look at the top and the bottom. You can see the interaction effects, all diagonals, but now that we have a third dimension, these are all diagonals on a plane. And then we've got a three-way interaction, which gets kind of confusing as we're tracing these little stars inside of the box. So this is the big piece that we're finally getting to, is this particular design. And again, this is one of the whole reasons we're making this video. We'll draw this out in a second. But as we look at this, this says factor A, B, and C are all at the low level. We have a couple replicates, and then we can look at the total value. Note that when A is at the high level, B and C are at the low level, then the lowercase Latin characters that are representing this is just A. Reading this, A's at low, B's at high, C's at low. We'd expect the Latin character to be B. That's what it is. A's at high, B's at high, C's at low. So we have A, B, and so on as we're reading through this. So looking at this particular case, again, we can see this table of factors. Now we can also do this for interactions. So actually, let's go on this chalkboard and draw this out for the interactions. So I'm going to have, let's draw out these different runs. 1, A, B, C, AB, AC, BC, and ABC, and you can call these runs 1, 2, 3, 4, 5 if you want to. Numbers don't really matter. And then we're just going to copy what the textbook had here, or what the slide deck had here in terms of the letters. So for A, minus, plus, minus, minus, plus, plus, minus, plus. So pretty much what I'm looking at is wherever there is an A, then it gets a plus sign. Whenever there's not an A gets a minus sign. Same thing with B. Whenever there's a B, it gets a plus sign. Whenever there's not a B, it gets a minus sign, and that's literally all I'm looking at when creating this table. Each of these should have 4 pluses and 4 minuses. That's a good double check. C, we have minus, 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 plus, minus, plus, 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 and there are 1, 2, 3, 4 plus signs. Now how we create these interaction terms is we literally kind of multiply the columns. So I'm going to take this column from A and this column from B and kind of multiply these two together. So a negative times a negative is a positive times a negative is a negative, a positive times a negative is a negative times a negative is a positive. Positive times positive is positive. Positive, negative, negative. Positive, negative, negative. Positive, positive, positive. So that was multiplying the A values times the B values to get the AB value. For AC, we're going to multiply the A value times the C value. So negative times a negative is a positive. Positive times a negative, is a negative. Positive, or negative times a negative is a positive. Negative times a positive is a negative. Positive, negative is negative. Positive, positive is positive. Negative, positive is negative. Positive, positive is positive, and I'm going to double check real quick. I've got 1, 2, 3, 4 plus signs. 1, 2, 3, 4 minus signs. So now we can go on to BC. So I'm going to be multiplying B times C together, and you can pause this and give it a shot on your own if you want, and then play. Minus, 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 plus, plus, and then our last interaction effect is the three-way interaction effect, A, B, and C. A minus times a minus times a minus is a minus. Plus, minus, minus is plus. Minus, plus, minus is a plus. And then one more plus, minus, 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 plus. And again, I can check that I have 1, 2, 3, 4 plus signs, and 1, 2, 3, 4 minus signs. So this is how we can construct these tables, and these will be very important once we get to the next chapter. So the properties of this table. So we've got the column, and I guess I didn't mention I should write this on here. That's a big oversight, so let me move everything over. I apologize. One other column that we need to write on here that wasn't in the books table is the identity column, plus, 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 plus. So I is just all pluses. So that's an important column. I apologize for forgetting that. So except for this identity column, every column has an equal number of pluses and minuses. Now if you add up the products of any two columns, this is 0. So that is, if you multiply any two, pick the interaction columns, pick whatever, multiply any two columns together, you should get 0. Multiply any two columns together and then add them up, and you should get 0. Multiplying any columns by the identity leaves it the exact same. And then when you multiply any two columns, when you're multiplying the letters, anytime you see the letter twice, so like B squared, it kind of cancels itself out, so it goes away. So this is kind of like a mod 2 situation. So if I have A and B, that becomes AB. But if you multiplied AB times BC, the B squared goes to 0, and then we get AC. So again, anything that's in there twice kind of cancels. If you had like AB times B times BC, 2 of those B's would cancel, but 1 would be left, and you'd be left with ABC. So actually, what you can do on your own right now, go and try it. On that table, take the AB column and then multiply all those values times the BC column, and make sure that they give you exactly what's in the AC column. And that's a good way to double check that this is what's going on. The orthogonal design means that when you sum the products of any two columns at 0, it's actually a very important property in all our factorial designs. In a graduate level class, you would talk more about this. We kind of skip over this, but this actually is an important concept that's present in our designs. All right, so if we're looking at the different factor effects, this is something that we had earlier with the percent contributions, and in our table we can look at the different p-values we see. We have the 3 main effects, then we have the 3 two-way interaction effects and 1 three-way interaction effect. When we're interpreting interaction effects, we start at the top when we walk down. So the 3-way interaction effect isn't significant, so we can go on to interpret the 2-way interaction effects. AB and BC aren't significant, but AC actually is a statistically significant interaction effect, so we want to be careful about interpreting factors A and C. Factor B isn't involved, so interpreting the main effects of factor B is fine. Looking at this, we see that factors A and C, again, we're not going to touch their interpretation. Factor B is not statistically significant. So reading through this, actually factor B, AB, BC, and ABC are all not statistically significant. Pretty much everything that involves factor B, gas flow, doesn't appear to be contributing to our model. Then we can look at the different estimated coefficients. This is via a regression framework. Now, one idea that we're going to talk about in just a second is removing non-significant factors. So we pointed out earlier that B wasn't statistically significant, so maybe we want to run a model without B so that we can look more in depth at AC. And let's stop here and talk about that, because this is something that your textbook does, but we really need to provide a warning. Be careful about removing factors. There are lots of risks involved with doing this. And this can be a very inappropriate procedure statistically. In fact, it really almost always is. So when you're thinking about removing a factor, we'll talk through a couple ideas just on this slide together. But as far as this discussion goes, if there's a good reason for a factor to be in a model, that factor should stay in the model, whether or not it's statistically significant. Again, there's a lot of risks, things like overfitting, models. That's the primary risk going on here, where we're keying our model too much to our data. You can avoid this by recommending the removal of the factor in a future study, but not actually looking at the results in your study. That's a very good and valid option. But you just really want to be careful when you're considering doing this. That said, when doing this exploratory type of analysis where we're just trying to figure out which factors are important, removing factors that aren't related to the outcome actually can be helpful. So we're kind of assuming in these types of studies is that there's a few factors that are related and that there's a lot of factors that aren't related. So getting rid of those trash factors that really aren't related can be helpful. So this is the second case where for this specific instance of statistical analysis, this procedure might be okay, or might not have some of the issues that we'd be careful with. So kind of like changing our alpha, this is something we would tend to avoid under normal circumstances, but for this specific circumstance where we're digging through a ton of trash factors and trying to find a few good ones, this does kind of make sense. So when we're doing this, a few tips. First of all, leave in marginally significant factors. So let's say a factor has a p-value less than 0.2, but it's not statistically significant. That would be a factor that we would tend to leave in. In fact, when we're removing factors, we tend to start with ones with the highest p-value, not lower p-values. Go one at a time. So when you're removing factors, you start with the one with the highest p-value, and then you kind of drop down to the next highest p-value and drop down to the next highest p-value. But don't remove, say, the top three factors altogether. What you would do is you would remove the one, then move to the next model, run it again, and then look at the p-values again, and then remove the next one, and then run it again, etc. Another interesting thing here is, but now that we've talked about interaction effects, if the interaction is statistically significant, you should not remove the main effects. I'll say that one more time. If the interaction is statistically significant, you should not remove the main effects. So let's say in a particular case, the interaction between alpha and beta is statistically significant at the 0.05 level. You're going to leave the interaction in. Well, even if alpha and beta on their own are not statistically significant, their p-values are like 0.8, 0.91, so definitely high candidates to be removed, but their interaction is significant, you would not remove the main effects alpha and beta. Now, if alpha beta's interaction was very significant, and you had like a C or a gamma or something like that there, then you definitely could remove the third variable that's not involved with that interaction. But when an interaction term is significant, you shouldn't remove the main effects whose combination make that interaction term. First, if you wanted to remove those, you should remove the interaction term. So you'd need that interaction term to be non-significant, and then you could go and consider, again, remove the interaction term, rerun the model, consider if you want to remove any of the main effects after that. But only if that interaction term isn't significant or isn't marginally significant. I'm using p equals less than 0.2, but there's a lot of definitions there. So you can also go forward. So we're talking about starting with everything in the model and then removing some. It's called backward selection. You can also go forwards. There's a process called forward selection. Backward selection tends to be a bit better, and we're not going to go into detail here. You can check a regression class. I think we talk about it at the end of a regression class. After you're done, for the final tip, after you're done removing all of your different factors, one piece of good practice is to look at what's called a general F test, which tests a full model with all the factors in it and a reduced model with everything taken out of it. It's good practice to compare those to make sure you didn't go too far and remove a lot of the variation that you were explaining in the full model, just my small increments that in and of themselves weren't statistically significant, but taken as a whole jump that was statistically significant. So I would definitely recommend the general linear F test when you're at the end of removing factors. And again, we're not going to talk about that in this class, but that's part of your regression class. So in this case, we chose to remove B, as we commented previously in the video. The interaction wasn't significant, and how we would normally do this is we would, the three-way interaction wasn't significant, and we'd need to take out the three-way interaction before we could take out the two-way interactions, before we could take out any main effects. So we take out the three-way interaction, we'd rerun the model, we looked at the AB and BC interactions, we took out the one with the highest p-value, we rerun the model, we look at the other one, we remove that, rerun the model, and then it turns out that B wasn't statistically significant after all that, so we remove B, and that leaves us with this particular table of our estimates. And again, this is through a correlation framework. So these Q-plots are nice ways in which we can express what's actually being done quickly. So you can quickly see what are the low and high values, and then what are the average values, or I think they use the sum values in this particular case for each one of these factors. Now, as you're considering factors and you're considering the different types of interaction effects, realize that you get a lot of interaction effects. So as we have K main effects, there's going to be K choose 2 factors, two-way interactions. There's going to be K choose 3 three-way interactions, etc. So there's going to be lots and lots and lots of interactions, and you can check the textbook for more details about that. Now, when 2Ks are unreplicated, this actually creates a bit of an issue. That said, it's kind of nice because you just have one observation in each area. So there's no real error term. It's tough to model noise. This is where those PP plots can come in. But this can be a really interesting design. If you're interested, I highly recommend checking out the textbook. But again, there are some risks that are associated with this when we only have one replication in each of the factor combinations. So when you're picking this, especially in the unreplicated design, it becomes really important. Note that the true factor effect, so for factor X and factor Y, or in the response Y, if we pick the plus and minus sign to be relatively close together, even though these two dots are kind of in the middle of their respective bars, we can see that the factor effect appears to be relatively low, and that's just because there isn't enough space to really determine that these two elements are different. But if we spread out the plus and minus signs, so the low and high, we can see a much larger estimate of this factor effect. So the big piece here is that when you're picking the low and high levels, you really want these low and high levels to be as far apart as possible. And this is a really big piece in the 2K design. This picture is actually a really great description. I really like this picture. It's one of the reasons we left it in. But it's a really great description as to why this is a big thing, because even if you did everything correctly, and even if there actually is a difference, even if that difference would normally be statistically significant, if you pick the levels of your factors wrong, you're going to not pursue this factor. And remember what we said earlier when we were changing the type 1 error rate, that missing a factor that's important is actually a big risk in these types of experiments. You really don't want to. So one of the ways by which you can avoid that is to place your different factor levels at the end of what is reasonably possible. Now, it's important for each of your factor levels to fall within reason. So these low values and high values shouldn't be absolutely ridiculously low and high, but they should should be as low as reasonable and as high as reasonable, as opposed to a couple values in the middle that you're just treating as low and high. So again, this lack of replication thing, there are some potential problems. One of the solutions, this normal probability plots, is kind of a really interesting approach. I highly recommend you check out the textbook to see kind of how they use our PP plots, which we've traditionally used to check normality, to study the different effects of the factors. It is kind of fun and interesting to check out, though we won't talk about it in this class. Now, because this is the exact same thing as factorial ANOVA, we're not going to have another R video in this. The next video we're going to have is going to jump straight into the fractional factorial design, using those tables that we wrote out and starting to play with those so that we can investigate how we can actually start to do runs of these experiments with smaller and smaller amounts of observations than we would normally think is possible.